Swayam Prabha. Digital India. Educated India.
Have to just watch it like a movie, okay? Don't have to worry about it. It's a story which I am going to tell you. So you'll have to listen to the story and think about it whenever you are actually at home or wherever you are and you are trying to basically do your day-to-day activities, okay? So I am Rajneesh. I am a faculty in the Department of Chemical Engineering. I am also associated with a School of Sustainability. This School of Sustainability is a new school in IIT Madras. It's roughly 6 months old now. What exactly it does? It basically brings people together from all the departments within IIT Madras, and we basically try to curate a course which would ultimately benefit the society by moving from unsustainable practices of today to sustainable practices of future. This is basically the idea, okay? And then not only we would teach, but we would also do some research which would basically ensure that the technologies which are supposed to be there for us to move from unsustainable practices to sustainable practices are there, and we understand it better, okay? Those are the two major goals of this School of Sustainability. There are many minor goals which we will not talk about it today because you all are school students. We will stick to the teaching and the research of sustainability school. Okay. Now, if you talk about processes which basically we use today, let me tell you, most of the processes which we use today, for example, if you are going to use a brush to brush your teeth, or the paste which you will apply on this brush to brush your teeth, these comes from certain processes, okay? These are called chemical processes, okay? So if I have to make a polymer out of a monomer, okay, I'll have to go into a process. If I have to make a monomer out of a chemical, so that I can build this particular monomer, I have to go into a process, okay? So the process typically happens not in one step, it happens in multiple steps. And if you are going to make any useful material out of all those chemicals which we know about water, we know about carbon dioxide, we know about formic acid, ethanol, methanol, all these small molecules which we know about, if we have to bring them together to make a larger molecule, and then this larger molecule has to polymerize together to make even a larger molecule, so that this polymer can be molded into a form of a brush. So I get a brush, okay? Now if I am using a brush today, during my, as soon as I get up, probably I'll try to go and brush my teeth. So we don't realize that this material which we have just produced or we have just bought from the market, how sustainable this material is, okay? We don't look into those aspects. Then we try to apply toothpaste on this brush. Now if we can apply a smaller amount of toothpaste, it's more sustainable compared to if I apply larger amount of toothpaste, okay? Or if I am going to take a bath, if I am going to basically use significantly large amount of water to take bath, it's less sustainable compared to if I am trying to take bath by buckets of water. So for example, I take a bucket and I take bath out of it rather than using the shower, okay? So it's more sustainable if I know how much water I will use to take this bath. 15 liters, 20 liters, depending upon how big is size of your bucket. You know exactly that this is the amount of water I am going to use if I am taking bath. If I am using shower, depending on my mood, if I am standing underneath that for 5 minutes or 10 minutes, I don't know how much water I have used. So it's not sustainable, okay? Now coming to using the soap or the detergent. Now soap, manufacturing of soap could be sustainable. Manufacturing of detergent could be made more sustainable, but then once you have used it, it goes down the drain, okay? Now the drain is now contaminated with your soap and your detergent. What you are going to do with that? It goes into ultimately it will go in some water body if you don't treat it. So is it sustainable to take bath every day by shampooing my hair? Not needed unless and until it's really dirty, okay? So this is some of the practices which every one of us has to think about to ensure that we talk about sustainability and we also approach our day-to-day activity in more sustainable way, okay? So this was some of the examples which I gave you. Now, if you would have heard recently, there has been a lot of talk about carbon dioxide capture, utilization and sequestration. Okay, why? Because people say that the kind of global warming which we are witnessing today has mostly come because of all the CO2 which has been being emitted from last roughly 100 years. Okay, after industrial revolution, we started using fossil fuel to a large extent. And when you use a fossil fuel, typically what is the portion of the fossil fuel which gives energy? Carbon and the hydrogen. Okay, carbon is high molecular weight compared to hydrogen. Tell me.
Molecular.
Carbon element has high molecular weight compared to hydrogen. So when a high molecular weight molecules come together to form something like coal, it's a density is high. Okay, because the interaction between two large molecules are much stronger compared to when hydrogen will come together to form a gas like hydrogen, because they are a small molecule. So the force of attraction between them is not that high. Okay, so when we talk about a hydrogen as a fuel, hydrogen gas as a fuel, it's a low density fuel. Okay, one hydrogen molecule and the other hydrogen molecule don't interact very strongly with each other. So they are low density fuel. When we talk about carbon, which has very high molecular weight, you see it basically when you talk about coal, it's a solid. It basically means that the density is high. Okay, so when the density is high, it gives you more energy if you burn a small amount of the sample. Okay, so this is why when we talk about a fossil fuel, we typically talk about coal, we typically talk about oil and natural gas. And if you look into this, if you try to make a correlation, you see coal is primarily carbon. So this is the most dense form of fuel, fossil fuel. Okay, then we go a little up and then we talk about oil, which is mixture of carbon and hydrogen. It's hydrocarbons. We talk about petrol, we talk about diesel, these are hydrocarbons. Okay, there are certain amount of carbon and certain amount of hydrogen. So when you add some hydrogen into this carbon, these molecules become, this end molecule become lighter, and from a solid you end up into a liquid. Okay, when things becomes lighter, it basically means the force of interaction will be slightly lower, then it will not be interacting too strongly with each other. So you see you had primarily carbon, coal is a solid, but as soon as we add hydrogen into it, we try to make it lighter and ultimately we end up in a liquid. Okay, so the density of that fuel is not as high as coal, but then the advantage of oil is that there is not lot of impurity in coal. So this is why overall if you see, oil is much better compared to coal, because when we talk about coal, we don't only talk about the carbon which makes the fuel, there are a lot of inorganic components in there, okay, which we don't really need, but that is part of the fossil fuel. So either we are burning coal, we will produce energy and we will also produce carbon dioxide. If you are using oil, we will produce again energy and we will also produce some carbon dioxide. Along with that, we will also produce some water, because there is hydrogen also part of the oil. Okay, so the net CO2 emission, if you talk about oil compared to coal, if I am going to produce 1 kilojoule of energy by burning coal, and if I am producing 1 kilojoule of energy by burning oil, which of these two will produce more carbon dioxide? Coal, because we have more carbon in there. And now if you move from oil to a natural gas, or let's say methane. What is methane? Methane is 1 carbon and 4 hydrogen. So you see this is even more lighter. There is very small amount of carbon in there and more hydrogen in there. So it's even more lighter. Now it's a gaseous molecule. So you see when you had single carbon, it was a solid. When you had 1 carbon and 2 hydrogen roughly, it was a liquid. And when you had 1 carbon and 4 hydrogen, it's a gas. Okay. So as I was telling you, hydrogen is a very light molecule. If you keep adding it on carbon, it will become much lighter. So the advantage of moving from coal to natural gas we were knowing long before. And this is why you will see most of these technologies which were using fossil fuel for generation of energy and doing its whatever activity. For example, if you talk about a car, which, for example, when we had a locomotive which used to burn coal, we moved out of coal. We said, no, this is not that sustainable, let's go to the oil. There we were producing lesser CO2, we were producing lesser amount of other effluents. So we moved from coal to diesel when we were talking about locomotive. Similarly, in car, we moved from oil to natural gas because natural gas is much more cleaner. But even after we have done all that, the CO2 emission is still increasing, okay, day by day. And this is what I will try to tell you, where the CO2 emission comes from, why it comes from, what we can do about it, and can we do some sustainable way of handling this particular problem. So I don't really see that in 1 hour I will be able to cover entire thing, okay. I am not going to rush through. I will give you a very simple, small concept, really fundamental knowledge about it, and I will leave it at that, okay. I am not trying to solve everything. Whatever I cover, I will try to cover in a way that you know everything, whatever I have covered. Sounds good? So far, whatever I have discussed, has there been any confusion on this? Perfect. So now let's look at, with this background, let me tell you, we are going to talk about what are CO2 emissions. Yes, please go ahead.
When we use oil or natural gas to produce the same 1 kilojoule, because there are hydrogens, we'll have to use more moles. But more amount of, like the same amount of coal, we'll have to use more than whatever coal we use. Will it still be lesser?
Yes, it will still be lesser because hydrogen also, see that energy comes from two different reactions here. One is carbon reacting with oxygen to produce CO2 plus energy, and the other is hydrogen reacting with oxygen to produce energy plus H2O. So if you are going to have some hydrogen in there, so overall for the same amount of energy produced, you are basically producing it from one reaction when you are using coal, that is C plus O2 going to CO2, while in the case of oil or in the natural gas, you are using two different sets of reactions, C plus O2 going to CO2 and hydrogen plus oxygen going to H2O. Sounds good? So in that sense, it would always be that when I am going to burn this oil or natural gas, the total CO2 emission to produce similar amount of energy is going to be significantly lesser than when we are trying to burn pure coal. Sounds good? Okay. There are other advantages which we don't want to go into the detail of what are the other advantages of oil and gas, but so far let's stick to the CO2 emission content. Okay, is that okay? Let's move on then. So the CO2 emission typically has come from all of these burning of fossil fuel, and the burning of fossil fuel is necessary every step. You take one step and you burn CO2. This is called CO2 footprint. Okay, anything you do, you are burning energy. For example, right now I am giving this particular lecture and the one projector is on there, so many fans are on, these computers are on, that monitor is on. Where all the energy is coming from? The AC is running. Where all the energy is coming from? It's coming from the same fossil fuel today. Okay. So every minute of our life we produce CO2. So unfortunately we cannot do much about it. We have to ensure that we make a process which is more sustainable compared to a process which was less sustainable, and this is why I gave you this example of coal to oil, oil to natural gas. Sounds good? So the amount of CO2 emission which is happening because of our need, and we will talk about later whether it's all the need or the greed, we will talk about the greed part later, but because of the amount of CO2 which we are emitting because of our need, that is day-to-day need, the amount of CO2 in the atmosphere is increasing day by day. So on average, the CO2 concentration in the atmosphere currently, what do you think is the number? What is the concentration of CO2 in the atmospheric air? Yes, don't go in percentage terms, such numbers are typically talked in ppm level, okay. So it says roughly 400 to 420 ppm of carbon dioxide, which you typically, ppm is part per million, okay. You talked about the percentage, similar number, but it's a different unit. So 420 ppm basically means that there is 420 parts of carbon dioxide out of 1 million other parts of other gases, okay. Now this is a number which is significantly high compared to when humans existed, say like 200-300 years back. Those days the numbers used to be 200 to 300 ppm. Okay, it basically means since industrial revolution, because of our need, our increased need, we have basically consumed significantly large amount of fossil fuel, and because of that the CO2 emission in the atmosphere is gradually going up, and today we are at 420 ppm, and if we don't do anything we might go beyond 500 ppm in very soon, because the rate at which CO2 is emitting today is probably the highest in our entire history. Okay, so it's not that we can go for another 100 years and there will be only another 100 ppm rise in the CO2 concentration. It might so happen that in another 10-15 years we would have added another 100 ppm of CO2 into the atmosphere. Okay, so the temperature which you see today, typically people complain about the temperature is soaring every day or it's going up. Typically people have connected the rise in the temperature and the change in the weather pattern to the amount of CO2 which is there in the atmosphere. So one of the reason why we are talking about all this is that there are ways which people think we should be able to basically control the amount of CO2 which we are emitting to the atmosphere. So if you look into this particular data, 41 gigatons of carbon dioxide was emitted last year. Last year, no, means year before last year, 2022. Okay, so 41 gigaton basically mean 41 billion tons. It's not 41 billion kilogram, it's 41 billion tons in 1 year. Okay, now you can imagine if you keep emitting this for many years, how much CO2 which you are going to emit into the atmosphere, and this CO2 is going to go to the atmosphere because of anthropogenic activities. Anthropogenic activity basically mean the activities which are related to human survival. Okay, not nature may emit lot of other much amount of CO2 outside in the atmosphere, but we are not counting that. We are only counting right now the amount of CO2 which humans are adding into the atmosphere. Okay, so long back when this kind of data was analyzed in 2018, and people predicted that the rate at which we are moving from fossil fuel to renewable and all, the amount of CO2 which we are going to emit into the atmosphere will peak somewhere around 2020. This was the expectations. But today the reality is that it has not peaked even today. And the last year maximum amount of CO2 was emitted into the atmosphere. Okay, so this is the reality. It basically means that even if we are expecting that we are moving from fossil fuel based to renewable based energy and we are moving really fast, it basically means that if the CO2 concentration in the atmosphere is still going up, it basically tells you that our demand is also increasing significantly. Okay, and the demand, the rate at which we demand more energy is more than the rate at which we are moving from fossil fuel based energy to renewable form of energy. Okay, this is the challenge. This is the challenge. This is why we are talking about all this. So if you look into this data, it's basically mean that we will have to do something drastic to reduce the amount of CO2 which is going to be in the atmosphere in near future. Now for this, there has been lot of conferences people have been attending. All the government, they are basically committing to certain numbers and all, and you know that India has committed to become net CO2 zero by 2070. Okay, India has committed to be net CO2 zero by 2070. It basically means that it's only by 2070 that all the CO2 which we are going to emit by all our processes and the CO2 which we are going to capture and sequester, all kind of things, there will be no net release of CO2 into the atmosphere. Okay, this is what we have committed, when by 2070 we are going to do that. But let's see how easy it will be or how difficult it could be if we have to achieve it by 2050, which is the target by US, and 2070, which is the target by India. China has committed to be net zero by 2060. So these are the moving targets. Certain countries want themselves to become net zero by 2040. Certain other countries have given themselves a target of 50. Certain other countries say that by 2060 will become, and India is one of the largest country which claims that we would become net CO2 zero by 2070. Okay. Now let's look at, are we preparing enough? or what kind of data, what are the data there, what kind of effort would be necessary for us to reach that 2070 target of net CO2 zero. Look at this number over here. This says that if I have to connect the CO2 emission to the global warming, how much CO2 I will be able to emit, for how many years I will be able to emit this CO2, that the global warming reaches 1.5 degree beyond what it used to be during the pre-industrial level. Okay. So, suppose at pre-industrial level, if the CO2 concentration was 300 ppm and the temperature those days were say 28 degrees centigrade on average, how many more CO2 molecule will add it to the atmosphere that the temperature from 28 degrees becomes 29.5 degrees as of today. This is the number. Or on the other side, you see that how many more CO2 molecules I will be able to add to the atmosphere that the temperature goes from average 28 degrees to 30 degrees. Okay, these are the two data which you currently see in this particular slide. So, depending upon those numbers, if you see we are emitting 41 billion tons of CO2 every year, it means that there is a 50% chance that if we add another 250 billion tons of CO2 into the atmosphere, we are going to cross this number. It basically means that if I am adding another 250 billion tons of CO2 into the atmosphere, there is a 50% chance that the global warming will reach from 28 degrees, which was pre-industrial level, to 29.5 degrees currently. Okay. And if I can only add 250 billion tons of CO2 into the atmosphere, considering we add 40 billion tons every year on average, it basically means that in another 6 years, we would have added sufficient carbon dioxide into the atmosphere that the global warming will go beyond 1.5 degrees centigrade or around 1.5 degrees centigrade on average. Is that okay? On the other side, if I have to target 2 degree rise, that okay, 6 years is too soon, I may not be able to achieve that. Let's target 2 degrees, 1.5 degrees is too tight, I am not able to achieve it. Okay. So, what I will have to do, I will have to again do the same calculation and see how many more years I have if I target for 2 degree rise in temperature rather than 1.5 degree rise in temperature. Okay. So, assuming that 41 billion tons of CO2 is being emitted every year, and let's assume that it is not going to go really high from here onward, we would see that that means that we have a credit of 1150 billion tons of CO2 which may go to the atmosphere till we hit this target of 2 degrees. Okay, that basically means that we will have to achieve this by 2050. So, basically this is the reason why countries like US have gone for this target of 2050, that we will become net zero by 2050, because by that time your global warming, your global average temperature will already be 2 degrees beyond the pre-industrial level. Okay. So, this slide tells you that we have already missed the bus for 1.5 degrees centigrade. We can't do much about it. But the question is that can we really do something so that we achieve this goal of 2 degrees rise in temperature compared to pre-industrial revolution. So, this is the data. Now, if I have to achieve this, what I will have to do? Okay. What I have to do, one option is that you stop using the fossil fuel, but does that an option? It's not an option. Okay. We use it, we are dependent on it. Our entire economy depends on the amount of fuel. For example, last year there was an increase in 8.5% increase in coal consumption by 8.5% for India. Okay. It basically means that every year we are growing at roughly 6-7% GDP. So, if I have to grow at that rate, if I am not really adding that additional amount of energy by renewable source, we will have to rely on fossil fuel. There is no other option. Otherwise, we will have lot of power cuts and all other challenges we are going to face, and government does not really allow you to do that, because they would say, okay, there will be lot of unhappiness in the country. So, they would say, okay, let's produce more coal, let's produce more energy. So, this is one of the reason why it's very difficult for you to really control the amount of CO2 which you will have to emit into that to the atmosphere. without worrying about your GDP and all other issues. Okay. So if I have to continue this practice, I need to be more sustainable. And how do I become sustainable? So if I look into power sector basically consumes significantly large amount of fossil fuel to produce what? Produce electricity. Okay, this is power sector. This typically India is coal-fired power plant, full with coal-fired power plant. 70% of our electricity gets generated by coal-fired power plant. Okay. So if you look into this, what we'll have to do in that sector, we will have to replace coal to renewables. What are the renewable sources we have? What all we can do? Yes. Solar, wind and all those things. This is what we can basically do so that we don't produce all our energy from coal, but majority of our energy from renewable sources, and that is supposed to, if I have to achieve that target of 2-degree rise, I'll have to basically roughly remove pretty much 60 to 70% of coal-fired power plant and replace it with a renewable source of energy. Okay, that's the first thing which you see from here. Now industry, if you look into the industry, there are other ways. One, either we move to renewable. The other option is that we keep producing energy from coal, but then we capture the carbon dioxide which we are emitting and we put it back under the earth, because this is where the carbon came from. Where we are getting all our fossil fuel from under the earth. So if I am getting it from under the earth, and if I don't really need the carbon dioxide and I only need the energy, why don't I just use the energy and put the remaining CO2 back into under the earth? So that will make it sustainable. I have got the carbon from somewhere, I am using it and I am putting back the carbon at the same location. Looks very interesting, looks sustainable, because I can keep doing it for really long time without any other challenge. So if I can achieve it, probably that will be a good option. So this is another way by which you will be able to basically achieve this net zero target, that whatever CO2 I am producing, I am basically capturing all the CO2 and putting it back under the earth. Okay. So this is what we can basically do, and the other option is to go to nuclear. Okay. If I am not able to do either of these two for whatever reason, the other option could be that I replace my coal-fired power plant with nuclear power plants. Okay, because nuclear power plants does not produce CO2. They don't produce CO2, they produce electricity without producing CO2. So these are some of the options which you have, and similarly you will have to go to each and every category and try to understand the pattern of that particular industry and understand what you will have to do to basically become net zero in each of these industry. So this is an exercise. For example, industry like cement industry, steel industry. These two industries basically contributes roughly 7.5% of carbon dioxide total CO2 in India each. Okay, around 67% comes from the power sector. Remaining 15 to 20% comes from just two big industry, that is steel industry and cement industry. These are the two commodities which you need when you are building a country. Right now we are building our country. Okay, so we need these two commodities very much, and both of these processes produces the significantly large amount of CO2. So what we have to do with that? There also we have to rely on CCUS. We will have to rely on, you see this one, the lighter blue color fuel switch. It means instead of coal, which currently might be used, we can move from coal to natural gas. We can move from coal to hydrogen. If we can do all that, I will be able to significantly reduce my CO2 emission from these processes. Okay, so this could be another option. What is the third really large block over here? Is energy efficiency. We have to rely on improving the efficiency of these processes. So for example, if 1 kilogram of steel currently produces, production of 1 kilogram of steel if currently produces say 3 kilogram of carbon dioxide, can we make it 1.5 kilogram of carbon dioxide by improving the efficiency of this particular process? If we can do that, it basically means that I have cut down my CO2 emission by 50%.
Sir, what is CCUS?
CCUS is carbon dioxide capture, utilization and sequestration.
How does that work?
We'll talk about it, don't worry. Okay. So in short, as I was telling you, what exactly it means is that all the CO2 which I am producing during the burning of the fossil fuel, I basically capture that carbon dioxide and put it under the earth or utilize in some other form, okay, so that it is not going to the atmosphere. So before CO2 is left to the atmosphere to get mixed with the other gases, you can capture the CO2 and put it under the ground or use it for some other purpose, or whatever CO2 is there in the atmosphere, you preferentially capture the CO2, utilize it or sequester it, is called CCUS. We will talk about it. Okay, I know I am running late, but let me quickly move on from here. So this is the challenge for power industry, for power sector, for industrial sector, for transportation sector, for buildings and for other transformations. All of this has to improve the total CO2 emission, which basically they will have to have a target and they will have to basically figure out where they will be able to cut down their CO2 emission. Unless and until you do it, you will not be able to basically reduce the amount of CO2 which we are going to send it to the atmosphere. And as you know, as the first thing I was telling you, we have a target. We have a target depending upon where you are. You have a target to achieve it by 2050 or by 2060 or by 2070. Okay, so we all are working to achieve or to meet those targets. Now let's look at, when we people talk about why can't we move from fossil fuel to renewables. Now this is the data. If you look into this particular data, if I have to put a straight line, I can put a straight line roughly over here, that is 20%. It basically tells me that in last several years, from 1985 to 2022, if I am looking at the energy users pattern of India, what do I see? That hardly 20% of the total energy is being produced by renewable, remaining 80% comes from fossil fuel. Have you heard of renewables in last 10-15 years? Many times. We keep talking about renewables. Even before you were born, probably we were talking about renewables even before that. And what we have achieved? This is what we have achieved. So it basically means that it's not that easy. If you have to have a target, you will have to work for it. Okay? Unless and until you have a target, you will not be able to achieve it. This is the only message I want to give. So if you don't work with a target, you will not be able to achieve it. Because typically what happens is easier to just dig under the earth, get the fossil fuel and burn it and produce the energy and then get away with everything. Okay, compare that to moving into a new way of producing your energy, and this renewable is talking about everything is added together. I don't know whether you are able to read it, but it's hydropower, solar, wind, biomass, waste, geothermal, wave, tidal, all the sources put together is only 20% today. Okay, and because of that, since we have not been able to basically convert our fossil fuel based infrastructure to renewable fuel infrastructure, you see the CO2 emission in India has started picking up from 1920, and today, as of today, we produce roughly 3 billion tons of CO2 every year in India. How much is this number? 3 billion tons every year. Okay, and you know at what rate it is increasing in India? It is increasing at 6% every year. At the rate of 6%, you see a small blip here because of the COVID, but other than after COVID, we have again bounced back and we are moving at really fast pace. That typically tells you that our growth is very good. Our GDP and all, this is what we are targeting is certainly working. But then because of that, the side effect is that our CO2 emission is also significantly high. So if you look into this number, we are the third largest CO2 emitter in the world. Okay, right now. And soon we might become the second largest, just after China. Okay, so this is a number which we need to worry about, because we also have to achieve a target of by 2070. So if we are just started peaking up, we don't know when we will basically reach the maxima. Are you getting my point? If something is going up, it will keep going up for really some time before it will start going down. So we are still rising at 5%, 6% every year. It basically means tomorrow it cannot become flat. There will be a momentum, it will keep going on and on. So we will have to basically target even more strongly if I have to achieve that 2070 target of net CO2 zero. Okay, you have some question? Not now. Okay, you can have more questions. Yeah, tell me.
So in the first graph, towards the 1985, the peak is higher and
Yeah.
it's a higher contribution. Why is that?
I'll tell you, I was a small child those days when I used to go to villages. I used to see huge amount of sustainable ways of producing, say, energy for cooking food. It may not be healthy, but it used to be sustainable. People were using biomass, people were using all kind of things. Either they were basically digesting the biomass to produce gas and using that for cooking, or they were basically just burning it directly and they were cooking. You see how much energy is consumed while cooking? Today, all of those households have been given a fossil fuel. We call it growth, but growth in one sense and going in wrong direction in other sense. You see, because of that, this has gone down, or many other reasons. Okay, so for example, most of all those places where we are using biomass, we have now pretty much replaced it with fossil fuel because it's cheap. You don't understand. You always think that it's expensive. It's not expensive. It's super cheap, and this is why we are using it. If we have to change the pattern of usage, the only other option for us is to basically make it expensive. There is no other way out. Okay, since we have super cheap fossil fuels available to us, we are using it without any thought. We keep using it. Did I answer your question? Okay, fine. So let's move on. So this is the, before I move on to the CCUS, as your friend has asked me to quickly go there, and I don't have much time, so I'll move. But I'll tell you, there are challenges. Please don't assume that as you move from coal to solar, everything will become fine. Okay, let me tell you what is the challenge of solar and why it has not really picked up so far. And probably since we are now forced, we are pushed to the wall, so we'll have to do something. But the problem is this. See, if I am talking about solar, producing energy from solar, how many hours I can produce energy from solar in a day typically? Roughly 6 hours. If you talk about an average in a year, it's roughly 6 hours every day. Okay. Now, if I am producing 6-7 hours energy, do we only consume energy for 6-7 hours? The remaining hours we don't consume? No. So, it basically means that for these 6-7 hours, when I am having sunshine, I'll have to produce energy for the remaining 18 hours of the day. Okay. Now, if I am producing electricity for the remaining 18 hours of the day, what I'll have to do? I'll have to store it. Because electricity, when it is produced, it has to be consumed. Okay. So, if you cannot consume it, you will have to store it. What are the options of storage of electricity you know about? Batteries. Okay. So, we will have to use batteries. What other options you know? You may not know about it, but the other option is to basically convert it into some other form of a chemical. And hydrogen is one such chemical which is very versatile. It's not only a fossil fuel, it's not only a fuel which you can basically burn to produce energy, it's an energy carrier, it's a chemical feedstock, and it's used everywhere. Without hydrogen, you basically, not a single molecule you will be able to basically synthesize, because hydrogen is required in most of our work. We always need hydrocarbon. Okay, it's the hydrogen and carbon we need. And if we do not have the hydrogen, it will be difficult for us to basically convert carbon to hydrocarbon. So, every process we talk about, we will need hydrogen. Okay. Now, let's look into this. If I have to produce 1 kilogram of hydrogen, 55 kilowatt hour of electricity is consumed in the electrolysis process which we know of today. Okay. The electrolysis process we talk about, where we will have to split water to produce hydrogen and oxygen. You know how much electricity is consumed there? 55 kilowatt hour of electricity to produce 1 kilogram of hydrogen. Okay. Now, if I have produced hydrogen, then now hydrogen has to be transported where it is needed. The solar panel might be somewhere else. The hydrogen might get produced over there near the solar panel with the electricity which you have produced. But then once you have produced it, you will have to transport it somewhere. Okay. And once you transport it somewhere, you will have to basically consume around 10 to 15 kilowatt hour of electricity for just hydrogen transportation. As I was telling you at the start of the class, that hydrogen is very small molecule. It's not easy for you to basically bring them together. So if you can't bring them together, you have to force them to come together. Okay, and force them to come together basically mean either you will have to go to a very high pressure to push these two molecules close enough to each other, or you will have to go to a lower temperature so that they try to come together by interaction between them and will liquefy. Because of all this, you will have to consume around 10 to 15 kilowatt hour of electricity for transportation of this 1 kg of hydrogen. So now add this 55 and another 10 becomes 65. Now 65 kilowatt hour of electricity which you have consumed to produce 1 kilogram of hydrogen and transport it to the site where you will use it. Now what you will have to do? If I have to produce back the electricity, because electricity is what is used. If I am not consuming it as a chemical feedstock, I will have to convert it back to the electricity. This is what we need. So if I have, because the remaining 18 hours you use the electricity to run these fans when the sunshine is not there. Okay. So you need electricity. Hydrogen will not run the fan as of today. You need the electricity to run it. So you will have to convert this hydrogen back to electricity. So 1 kg of hydrogen comes back only 30 kilowatt of electricity because of the efficiency of the process and all. So what we are trying to say that from the 65 kilowatt or 70 kilowatt which we basically consumed, we are only getting 30 kilowatt hour of electricity at the end of the day. Okay. So it means the process of hydrogen production from solar is not even 40% efficient. I have given 65 to 70 kilowatt of electricity and I am getting back only 30 kilowatt hour of electricity. And I am not even counting the other expenses and all. I am just talking about the process over here. Okay. So the question is that if I am going to produce, if I need 65 kilowatt of electricity to produce 30 kilowatt or whatever the way you try to look at, for the remaining 18 hours, you can imagine how much solar panel has to be put together to produce sufficient amount of hydrogen, which will be able to capture all the electricity which we need for the remaining 18 hours. The efficiency is not 1 to 1. Please be aware of that. This is one of the challenge. The second challenge is, if I am not going to use hydrogen, if I use batteries for it, where I am going to store this 18 hours of electricity in a battery, the amount of batteries required would be significantly large. Okay, and there also there will be efficiency process. Battery does not come out from thin air. Okay, you need certain molecules to basically produce that battery. Those molecules typically you get from places where you do not have, you have to mine lot of chemicals. Okay, mining of chemical will also have a CO2 footprint. So these challenges are there, and this is why it's not an easy target once you are trying to look at. So moving on, the second thing which I will tell you is that once you have captured the CO2, this slide I will come later. So when we talk about CO2 capture, I have maybe another 10 minutes. How many more minutes I have? Another 10 minutes is fine. Okay. Because I see most of the students are restless, they want to leave. They are already here for many hours. So, not more than 10 minutes. I will try to convey my message before and then after. See, if you have to capture CO2 from wherever we want to capture, there are multiple different approaches. As a chemistry guy or as a chemical engineer, I will tell you, it's a process which basically you will have to do lot of calculations to understand what works, what does not work. Okay. In this particular case, when you have a CO2 mixed with other gases, see the challenge here is most of the time when you are going to burn coal to produce electricity, burning of coal is a solid and you are going to burn it in another molecule which is a gas. Okay. So if I have a solid and if I am trying to burn it with a gas and the reaction has to be between one carbon and one oxygen, it's an inefficient process. And because of that, what we have to do, we have to pulverize the coal. Okay, pulverize the coal on one hand, and you are rightly saying you will have to pressurize the system with more oxygen. Okay, so because of that, we always burn this kind of fossil fuel with excess of air. Okay, there could have been two options. One, either I burn it in air or I burn it in oxygen. But since oxygen is not available unless and until you separate oxygen out of the nitrogen which is present in the atmosphere, whenever people decided to go about it, they said, okay, let's burn in the air. So pretty much every time you burn it in the air. So when you are trying to burn a fossil fuel like coal, which is solid in air, and to ensure that there is an efficient combustion between each of these carbon molecule which is present in the coal and the oxygen which you, or the air which you, oxygen from the air which you get to react it with, you have to do two things. One, you have to pulverize the coal, and the second, you will have to go to an excess supply of oxygen. And when you are trying to excess supply of air, it basically means when you are talking about air, you are feeding significantly large amount of nitrogen along with the oxygen, which is not participating in the reaction at all. It comes in and goes out pretty much. Little bit of nitrogen will get converted into NOx. Let's assume that this is not much of NOx being produced. So pretty much all the nitrogen which has fed comes out of the process. So what is a gas which we have to handle now? If I have to capture CO2, it's a mixture of CO2, nitrogen and leftover oxygen, assuming all other impurities are not there, just for the sake of assumption, because these are the large components which we are talking about. All other components will be in really a small amount. Okay. So what do we have now? We have a mixture of carbon dioxide and nitrogen and some oxygen. CO2 capture basically mean capturing carbon dioxide from this mixture. These are gases. So when there are gases mixed, they are mixing uniformly. In this room, there are all kind of gases mixed. I am saying that you capture CO2 from this room. Can you imagine how difficult it would be to capture CO2 from this room? This is exactly the challenge we are facing over here. We are talking about, don't worry, let them sleep, that's okay. What I am trying to tell you is that the composition of the gas which we are handling here is CO2 is much lower quantity and nitrogen is in very large quantity. Okay. Now the challenge is CO2, which is a larger molecule, significantly larger molecule compared to nitrogen, can be easily captured. But just because nitrogen is present all around your CO2, it's difficult for you to capture CO2. Okay. Nitrogen is one molecule which has huge amount of kinetic energy at room temperature. It just keeps moving here and there because it's a small molecule. CO2 on the other hand is a large molecule. It does not have so much of kinetic energy. So theoretically, you can capture CO2 easily by interacting with some molecule. But what happens in the company of this bad guy nitrogen, this CO2 starts behaving like nitrogen. This is the challenge, because nitrogen will come and bombard the CO2 molecule. So the CO2, which was not having enough energy, is now moving at a much faster energy because of the nitrogen all around it. So this is the challenge. If I have to capture the CO2 from a mixture of nitrogen, oxygen and CO2, where CO2 concentration is significantly low, it's not an easy work. Okay. This is in simple term, this is what I'm trying to tell you. Now, if I am talking about CO2 coming from any fossil fuel power plant, it's roughly 10 to 15% CO2, remaining being nitrogen and oxygen. Easier to capture CO2 from there. What is the challenge though? The challenge is these gases are not the only gases which you will get coming out from a power plant. Okay, there will be some molecules like SO2, there will be different versions of NOx, okay, and there could be carbon monoxide and all other kind of particulate matter, and because we are using a pulverized coal, so when it will burn, it will come along with the gas also, so a lot of particulate matters also is there. Now these impurities basically makes this process even more complicated, because whatever material which you are going to use to capture CO2, okay, you have to understand it this way. I have in this particular room one rogue element and I have to capture him or her. What I will do? I will ask few of you to go and capture him or her. This few of you is the material we are talking about. If I have to capture CO2, I cannot capture CO2 from going and just catching it. I need a material which will go and interact with CO2 and will hold it to itself. Okay. So now the question I am asking you, and this is when I will pretty much stop here. The question I am asking you, how many CO2 molecule I told you that I am leaving to the atmosphere every year? 3 billion tons in India. So how many that material we would need which will capture this CO2? Typically, any material we talk about which will capture CO2 will have a capacity of roughly 10%. If one person is running around here at really fast speed, can you do it by one person, that one person will go and catch him or her? Not possible. No, 10 of you might need to capture that particular person. So it's very simple. Similar analogy, if you look at, if I'm talking about a rogue element CO2, which is present along with the nitrogen and oxygen, if I have to capture it, I need another person, and not one person, probably 10% to capture this particular guy. This is the challenge. So if I am producing 3 billion tons of CO2 every year, imagine how much that material will be required. 30 billion tons of CO2 of that material. Now 30 billion tons of that material, if you are going to produce, how much CO2 will produce to produce that material? Are you getting the challenge? This is the challenge. Okay, it basically means I have to do two things. One, I have to first identify the right material which will do this job through research, obviously, and then I will have to recycle this material 1,000 times, 10,000 times. That's the challenge. That is what we try to do. When we go into the lab and we work with our PhD students, we try to do all these simple things. If you look at carefully, it's not that simple, it's not trivial, it's complicated. You'll have to solve some of these complicated problems together and to basically achieve some of these things. Anyway, so if I have, depending upon what is the concentration, I will just give you this particular, suppose I have captured the CO2 by this particular material, whatever you talk about. Capture the CO2, what I am going to do with this CO2? I'll have to sequester this CO2. Sequestration and storage is two different words. Sequestration means the CO2 which was mobile, being in gaseous phase, has to be made immobile, either being converted into liquid or into a solid. This is called sequestration. And storage means I will store it somehow. It might be in gaseous phase, I will store it. But there is a possibility of this CO2 leaking out back to the atmosphere if I am just storing it. Okay, so this is the difference. Now many people say, hey, why we will have to sequester it in under the earth and all kind of thing. Why can't we plant more trees to sequester the CO2? That's the easier one option. Let's look at how easy it is. Let's look into the maths. If one does the math, we need to capture 20 billion tons of CO2 every year up to 2050 to achieve 2-degree scenario. This is what I gave you. Okay, we have to capture 20 billion tons of CO2 every year till 2050 to achieve 2-degree rise. And we have to keep doing it. It's not that we will have to stop it after 2050. Now, 1 hectare of forest typically captures 10 tons of CO2 or sequesters 10 tons of CO2. 1 hectare of forest sequesters 10 tons of CO2. World over, 2022 alone, 40 billion tons of CO2 got emitted. So, basically to capture the entire CO2, I need 4 billion hectares of land. How much total land we have on earth? We have only 15 billion hectares of land on earth. It basically means that in 4 years I will be able to, I will cover entire earth with plants and trees, and the 5th year where all the CO2 will go. This is the challenge. You will not believe the amount of CO2 which we emit, and this ends the discussion today. This is the challenge, which is what we have to, this is why India has given a target 2070. Don't know what will happen, but the point I am trying to make, it's a very difficult problem to, and for one important point, and after that I will end this particular class. I talked about the word need. Okay, when we say we need it because this has become our lifestyle, it's a challenge. Okay, I will try to give you a few examples. You talk to your parents and ask them how many pairs of clothes they used to have when they were kids like you. They might tell 4 pairs, 5 pairs, 6 pairs. How many you have? Go and count 30 pairs, 40 pairs. Do we need all of that? Is that a need? It's a greed. Okay, that's not need. How many pairs of sandals and slippers which you use at home? Go and count. You might have 50 pairs lying at in your all this put together. I'm not talking only you. Do we need all of that? It's not need, it's greed. Okay, when we talk about having sustainable buildings and all, obviously Chennai is slightly hotter day by day, but if I have 3 different monitors running here, do we need all of that? Not. One monitor might also have been sufficient, no? But we are doing it. If I put a large monitor here, if I design this room properly, can't all of us see in one monitor? Instead of that, we'll have to run 3 different separate monitors. So these are greed. Please differentiate between the need and greed. That's all I'll tell you. So what you have to do as a student, differentiate between the need and the greed. Stop your greed, go only for the need, that itself will reduce our CO2 consumptions by 20-30, CO2 emission by 20-30%. None of this technology will be able to deliver that, what you can deliver. Okay, because we are the people who are emitting and it's our responsibility to reduce it. Okay, any questions?
Sir, once we plant, if hypothetically plant trees in this 4 billion hectares, won't they continue to sequester carbon? Why do we need to plant every
No,
year?
does not continue to sequester carbon. When plant grows, it requires that much of CO2. You see, this is a process, no, as I was telling you. Once you have already grown, you will need a smaller amount of food. When you grow, you need lot of nutrients to grow. Okay, but once you are already 60, you have to cut down your food, otherwise you will die soon. Too much of cannot be. So these are the challenge. Obviously, what you are saying is right, that to certain extent it will still capture the CO2, but will it capture 40 billion tons, which we produce every year? It will not. That's the challenge. Okay. There are other ways of doing it. You can cut down the tree and replant it, cut down those trees and burn it and use the energy. All those are possible. Okay. I am just giving you a simple example. Just tell me.
I was about to ask that what happens when the plant dies, like the tree dies?
That
So-
CO2 comes back to the atmosphere. Yes. So, but the thing is that if I am cutting it deliberately and using it as a source of energy, then I am not adding any additional CO2. No, sorry. I used to get otherwise from under the earth, which I am adding to the atmosphere. But if I am using the same CO2 which is part of the atmosphere to grow the tree, and then I am cutting the tree and again producing the CO2, I am not bringing any new molecule from under the earth. That's the difference. Okay. But yeah, those things are supposed to be debated, whether it's possible, how much it is possible, all those things are there. Okay. If I plant everywhere trees, where I will live? On the top of the tree? That also has to be worried about, no? Because there is only 30% of the land which we have, as so many people, we need the space for them also. So we cannot just say that everywhere we will plant the tree and we are going to live on top of it. Okay, good. Have a nice day. I hope most of you were awake, few of you were sleeping, but that's okay, I don't mind.